Welcome! Today we are going to solve a physics puzzle that you see every single day, from the fan on your ceiling to the satellites up in the sky. We're diving into something called uniform circular motion, and we're going to figure out how something can be moving at a constant speed and still be accelerating.
So let's kick things off with a big question. We all know satellites are just whipping around the Earth at these incredible speeds, but what's stopping them from just, flying off into the blackness of deep space? What's holding them in that perfect circular path?
Okay, so the first piece of the puzzle you've got to get your head around is that in uniform circular motion, the object's speed is constant. If a satellite speedometer reads 17,000 miles per hour, it stays locked right there. It's not speeding up, and it's not slowing down.
And right here, this is where things get a little weird. This is the paradox. We're all taught that acceleration means a change in speed, right? Hitting the gas or hitting the brakes. So if the satellite speed is totally constant, how in the world can it be accelerating? It feels like it breaks the rules, but it doesn't.
The solution is hidden in the difference between two words we often use interchangeably: speed and velocity. See, in physics, they're not the same. Speed is just a number. It's how fast. But velocity? Velocity is speed plus a direction. And that little detail, the direction, changes everything.
I mean, think about it. To move in a circle, an object has to constantly be turning. At every single instant, its direction of travel is changing, even just a tiny bit. And if the direction is changing, that means its velocity is changing, even if its speed isn't.
And this brings us right to the big reveal. The true definition of acceleration in physics is any change in velocity. It could be a change in speed, sure, but it can also be just a change in direction. And since our satellite is always changing direction, it is, by definition, always accelerating. And just like that, the paradox is solved.
Okay, so we've established there's an acceleration happening. But that just brings up another question, doesn't it? What's causing this constant turn? There has to be some kind of force that's pulling the satellite away from the straight path it wants to follow.
Well, this is where we meet a new concept. It's called centripetal acceleration. And it's a very specific kind of acceleration that is always pointed inward, right toward the center of the circle. Its entire job, its only mission, is to change the object's direction, not its speed.
And as Sir Isaac Newton taught us, if you have an acceleration, you absolutely must have a force causing it. And the force that's responsible for this centripetal acceleration is, you guessed it, called the centripetal force. This is the real-world push or pull that makes the whole thing go in a circle.
The word centripetal itself is a huge clue. It literally means center-seeking. So you can picture it like an invisible rope constantly pulling the object toward the center and stopping it from flying away. For our satellite, that invisible rope is Earth's gravity. And what's really cool is we can actually calculate this force. To do it, we just need to know three key things: m for the object's mass, how heavy it is; v for its tangential velocity, that's just a fancy way of saying how fast it's moving along the curve; and r for the radius of the circle it's making.
And here's the formula. It looks simple, and it is. The centripetal force equals the mass times the velocity squared, all of that divided by the radius. Now, the part you really got to pay attention to is that the velocity is squared. That's a huge deal. It means that an object's speed has this massive, outsized impact on the force needed to keep it turning.
So once you really get this idea of a center-seeking force, you'll start seeing it absolutely everywhere. It's in the smooth sweep of a clock's second hand, the spin of a fan's blades, and yep, it's the exact same principle that keeps moons, planets, and entire galaxies locked in their cosmic dance.
So, let's end this with a fun thought experiment. Imagine our satellite orbiting perfectly, held there by Earth's gravity. Now, what would happen if we could just snap our fingers and turn gravity off? Poof, gone. The satellite wouldn't just stop. It would keep moving at 17,000 miles per hour and fly off in a perfectly straight line tangent to the circle it was just on. A perfect little demonstration of inertia and the incredible power of this center-seeking force.